Okay, so for the first worked example, this will be to determine the number of protons, neutrons, and electrons in each of the following. There's going to be 4 different parts. The first one is looking at chlorine 35. It gives a full nuclear symbol. The top number is the mass number, and the bottom number is the atomic number. The mass number represents the sum of the protons and neutrons together. The second example, which is chlorine 37, you'll notice that there's not an atomic number listed, and you can still figure that out just by looking at the periodic table. And they count 1 up to over 110, and each one of those individual digits represents the atomic number and is equivalent to the number of protons. Potassium 41, you just get a mass number. Again, you can use the periodic table to find the atomic number. And the last one is written out by name, carbon-14. The -14 is dash mass number, so this would be like the superscript number. So just like the first video, we go through an example. You can pause the video and work through it, and then come back and look at the solution. So same thing with this one. The strategy from this, and again I mentioned this as we were just talking about the 4 problems to work through, says to recall the superscript denotes the mass number, and the subscript denotes the atomic number. If no subscript is shown, the atomic number can be deduced from the element symbol or name, just right from the periodic table. Last thing, I haven't mentioned this yet, but atoms that are neutral will have an equal number of protons and electrons. So for all of these examples, the atoms are neutral, so the number of electrons equals the number of protons. Alright, so hopefully you've had some time to work through this if you paused the video. If not, you just wanted to follow along and see what to do. Let's look at the first one in part A. Chlorine's atomic number is 17. That represents 17 protons. The mass number is 35. If we find the difference between the mass number and the number of protons, we get the number of neutrons. This is 35 minus 17. That's equal to 18 neutrons. Since it is neutral, the number of electrons and protons will be the same, so this will have 17 electrons. For part B, chlorine's atomic number is still 17. Atomic numbers are constant, so again there's 17 protons. The mass number is 37, so the mass number is different. If we find the difference between 37 and 17, we get 20 neutrons. So this would be an isotope of the other chlorine. Isotopes only differ based upon their number of neutrons. Again, all of these examples will be neutral, so you should have an equal number of electrons and protons. So this will have 17 electrons. All right, for part C, we're looking at potassium 41. Potassium's atomic number from the periodic table is number 19, so that would be 19 protons. That noise in the background is my dog, so excuse that. Anyways, the mass number is going to be 41, which we get right from the given. If we find the difference, 41 minus 19 is 22. That will give us the number of neutrons. In this case, is 22 neutrons. The number of electrons, pretty easy. It's neutral, so it's also 19 electrons. Part D, need to know carbon's atomic number. We can get that right from the periodic table. Atomic number is 6. It's equivalent to 6 protons. The mass number is 14 from the given. Find the difference. 14 minus 6 is 8. That gives us the number of neutrons. Again, all of these examples are neutral, so this will have 6 electrons. This next slide is not a worked example, but it does have some useful information on it that I wanted to go through, especially the conversion. So this is on nuclear stability, and it talks about how the nucleus contains most of the atomic's mass. Within the nucleus are the protons and neutrons. Also, the stability of the atomic nucleus can be related to density. Density is going to be a physical property which relates mass per unit volume, which is mass usually in grams divided by volume in milliliters if it's a liquid, and even if it is a liquid, but if it's a solid or gas, that's usually represented in cubic centimeters. So this is looking at an example of a nucleus with 30 protons and 30 neutrons. And we're going to do a density calculation here. So R represents a radius, and this radius is starting with 5 times 10 to the negative 3 picometers. So it's going to be converting some units with prefixes that you may not be familiar with, something not as common as a centimeter or a decimeter or a micrometer. So a picometer is going to be equivalent to a really small meter, 1 times 10 to the negative 12. This can also be converted to centimeters, and the reason why we want to use centimeters is because we're getting to a common density unit of cubic centimeters. So taking this radius, and this radius, it looks like it comes out of just thin air, but it would be given. So this would just be a given radius, 5 times 10 to the negative 3. And the ratio is set up with meters in the numerator, picometers in the denominator. Just like in the last video with conversions, picometers will cancel. The next conversion takes 100 centimeters in the numerator and 1 meter in the denominator. Meters cancel. This leaves us with centimeters. Performing this math, we get 5 times 10 to the negative 13. So this just moves our decimal place to go from picometers to centimeters. Okay, so now let's look at density. Density is going to relate mass per unit volume. Again, this mass would need to be given. So this is taken 1 times 10 to the negative 22 grams and divided by 4/3 pi r cubed. 4/3 pi r cubed represents the volume of a sphere because these are spherical in shape. So we have our mass on top or in the numerator, 1 times 10 to the negative 22 grams, divide by 4/3 pi. Pi is a constant in our calculator that we all know is 3.14. And then multiply that radius from above and make sure that is cubed. So that's going to cube not only the unit but the numerical value. All of the math here, and it's not a bad idea to pop this all into your calculator, make sure you can get this same value or something close to it if there's any rounding in this slide. Comes out to be 2 times 10 to the 14 grams per cubic centimeter. Some interesting tidbits from that is that the highest known element density is 22.6 grams per cubic centimeter. However, the average atomic mass is roughly 9 trillion. And that's going to be 9 trillion times as dense as the densest element known. So pretty interesting. Very, very dense. That means that it's extremely compact altogether. Alright, so now for a second worked example. Let's just read this. Oxygen is the most abundant element in both the Earth's crust and the human body. The atomic masses of its 3 stable isotopes, again, isotopes only differ based upon their number of neutrons. So the atomic masses of the 3 stable isotopes, oxygen 16, oxygen 17, and oxygen 18 are, and then it gives those 3 masses and lists those in AMUs, which is atomic mass units. Also listed are the relative percents. If we add all 3 of those percent values up, which are here that I've just highlighted, that should come out to be 100. Calculate the average atomic mass of oxygen using the relative abundances given above. So, strategy for this. Each isotope contributes to the average atomic mass. based on its relative abundance. Multiplying the mass of each isotope by its fractional abundance, which is a percent value divided by 100, will give its overall contribution to the average atomic mass. In the periodic table, each one of the squares is going to have the elemental symbol right in the middle. Usually most periodic tables will have the atomic number, which is a whole number, on the top, which represents the number of protons, and down at the bottom is the atomic mass. The atomic mass are not whole integers, but actually will have decimal places with it. And the reason why is because each of those atomic masses are determined from multiple isotopes of the individual elements. So, for example, when we're looking at oxygen, in this one, we'd be looking at these three isotopes of oxygen, the relative percent abundances of each, and then we can ultimately figure out the overall average atomic mass, which is what would be listed in the periodic table. Okay, so let's take a look at this. This is 0.99757 is just the percent divided by 100. It just makes this a fraction. Multiply by that respective atomic mass unit that was given with that percent, and then add that to the second mass unit multiplied by the percent divided by 100, and the same thing for the third one. So we would multiply through first, and then add all three of those together, and it should come out to be 15.9994 atomic mass units. So then the take-home message would be the average atomic mass should be closest to the atomic mass of the most abundant isotope. In this case, it would be the oxygen 16. Oxygen 16, you can see, is 99.757%. And again, it's 0.99757 here because when you multiply a percent, you want to do a 100th of that. Keeping true to the significant figures, we get a value with 4 decimal places, and this should be relatively the same number that appears in the periodic table. Some of the periodic tables don't go to 4 decimal places out. A lot of them will do 16 for oxygen, which has just been rounded to that 4 significant figures. Okay. Let's take a look at a third example. Just read through this first. Calcium is the most abundant metal in the human body. A typical human body contains roughly 30 moles of calcium. Determine A, the number of calcium atoms in 30 moles of calcium, and B, the number of moles of calcium in a sample containing 1 × 10 to the 20 calcium atoms. Strategy here is going to be using Avogadro's number and Avogadro's constant. Avogadro's constant is 6.022 × 10 to the 23rd, and that value always stays the same, and what that is equivalent to is 1 mole. Don't make it more complicated than it is. Use it just like you would a dozen. We know that a dozen is 12. So if I had a dozen apples, I would have 12 apples. Avogadro's number is equivalent to 1 mole. A mole is a chemical counting unit, like a dozen is very commonly used for bakers, like a baker's counting unit, and that we use for eggs. So to go back to my example, I said if I had a dozen apples, that would be 12 apples. If I had a mole of apples, I would have 6.022 × 10 to the 23rd apples. Alright, so usually we're not going to use a mole of apples. The mole is going to be applied towards chemistry concepts. So this is very common to use to calculate moles to atoms and atoms to moles. So for our solution to part A, we start with 30 moles of calcium, and we're going to work through this just like I would or you would for a conversion problem when you're converting units. So we're converting here from moles to atoms. So our conversion factor is going to use Avogadro's number in the numerator and moles in the denominator. moles cancel, and we're left with 1.807 times 10 to the 25th calcium atoms. For part B, 1 times 10 to the 20 calcium atoms, we're starting with atoms, and so this time you have atoms, which is Avogadro's number in the denominator, moles on top, atoms cancel, and we're left with 1.66 times 10 to the negative 4 moles of calcium. Just some terminology so you can wrap it around in your mind. If you have moles of an individual element, the individual pieces will be atoms. If you have moles of a compound, the individual pieces will be molecules. You will still use Avogadro's number for atoms if you're going from atoms to moles or moles to atoms. You will also still use Avogadro's number to go from molecules to moles of a compound, or moles of a compound to molecules. One message just to think about before we go on is to make sure that units cancel properly in each of our answers and that the result makes sense. So in part A, the number of moles, which is 30, is greater than 1, so the number of atoms is greater than Avogadro's number. In part B, the number of atoms is less than Avogadro's number, so there is less than 1 mole of a substance. Fourth example reads, determine A, the number of moles of carbon and 25 grams of carbon, B, the number of moles of helium and 10.5 grams of helium, and C, the number of moles of sodium and 15.75 grams of sodium. Our strategy here is going to be using the molar mass of an element. The molar mass is going to be that value that is on the bottom in the periodic table. Usually, you have your symbol. The top number is atomic number. The bottom number is our atomic mass, also sometimes called the molar mass. The reason why it's called the molar mass is because it represents how many grams that substance would be in 1 mole of that substance. So the molar mass of an element is numerically equal to its average atomic mass. We're going to use the molar mass for each element to convert between mass and moles. Alright, so setup for these. In part A, we're going to use a molar mass of carbon, which is 12.01 grams per 1 mole. So in the periodic table, that's where you would get the 12.01 from. The other number that is associated with carbon is 6, which is the atomic number. Now, don't confuse the atomic mass or molar mass with the mass number. Mass number is a whole value, which represents protons and neutrons. Atomic mass is different in that it looks at the most abundant isotopes and their relative percents, just like that oxygen example we looked at a few moments ago. Alright, so if you look down at the solution for part A, we were given 25 grams of carbon. We're going to use a conversion from the periodic table. The atomic mass of carbon is 12.01 grams. 1 mole on top. Grams will cancel, and we're left with 2.082 moles of carbon. For part B, we need to look up the molar mass of helium from the periodic table. That should be about 4.003. The units associated with it are grams per 1 mole. And then they're all grams per 1 mole of whatever element you're looking at. So the math here is 10.5 grams. We want to multiply by the ratio of the moles and grams. Grams cancel. We're left with 2.623 moles of helium. In the last example with sodium, the molar mass is 22.99 grams per mole. Again, that comes straight from the periodic table. We set it up with this ratio. Grams cancel, and we're left with 0.6851 moles of sodium. One thing to remember just with conversions, you have to determine what goes on the top or in the numerator and what goes in the bottom or the denominator. If you have to put one on the top or bottom, don't change the numbers around. Make sure the numbers and units stay with each other. So like 1 mole stays with the carbon, it doesn't switch to 12.01 moles. Okay. One more thing. Always double check your units, make sure that they cancel. It's very common to not have them cancel. As I mentioned in the conversion video, it's not a bad idea to set it up just with units first. Make sure you can get your units to cancel, then go back and put in the numbers. And just take your time with it and do it in a stepwise fashion. Okay. So here's a slide that I do want to go through. It shows you how to convert from grams to moles to individual units. And it shows what you would be using as your conversion. So let's first look at how we go back and forth between grams and moles and grams. If you're going from grams to moles, you divide by the molar mass. The reason why is we want to get to moles and cancel out our grams. If you want to go from moles back to grams, you multiply by the molar mass. Notice here the moles would cancel and you'd be left with grams. So convince yourself that both of these conversions work to go one way or the other. Now applying Avogadro's number, we'll go from moles, which is our chemical counting unit, into our individual pieces. Our individual pieces are usually particles, atoms, molecules, or formula units. For the most part, we'll be using atoms or molecules. To, for example, atoms, we will take this relationship of Avogadro's number in the numerator, moles in the denominator. Moles cancel out, we'd get our atoms. If we're going from the atoms, molecules, or particles back to moles, then you're going to do the reverse, or the inverse, with moles in the numerator and the Avogadro's number in the denominator, so that it cancels and leaves you with moles. Let's look at one more example to apply that and take some time to practice. Make sure you pause the video and give it a try before you keep watching. This reads, determine A, the number of carbon atoms in 0.515 grams of carbon, and B, the mass of helium that contains 6.89 times 10 to the 18 helium atoms. So in part A, we're looking for atoms, and in part B, we're looking for a mass. So our strategy is to use the conversions depicted on that last slide. So for A, we're going from grams to moles to atoms, and B, we're going from atoms to moles to grams. Our setup for part A, let's look at part A first. The molar mass of carbon is 12.01 grams per mole. That comes right from the periodic table. We're going to start with our mass, 0.515 grams of carbon. We're going to use the molar mass of carbon, which is 12.01. Notice how this is arranged so that grams of carbon cancel. Moles is in the numerator. If we stop there, we're left with moles, but it's asking us to take it to atoms, so we need to do another conversion using Avogadro's number. We set this up with moles in the denominator so that moles are canceled. Moles over moles is 1. And Avogadro's number is up here. We're left with 2.58 times 10 to the 22 carbon atoms once we put this in our calculator. Practice putting this in your calculator. Practice using the parentheses. When you put it in your calculator and you use the parentheses, like if you have a graphing calculator, you'll do parentheses 6.022. I usually use the EE button. So second, find that EE, and then you'd put in 23, and then close the parentheses. So one more time, parentheses 6.022 EE 23 parentheses. For part B, we're going to use a molar mass of 4.003 grams per mole. That comes right from the periodic table. So we start with the number of atoms of helium, which is 6.89 times 10 to the 18. And this time we have the inverse from above, and the reason why is so that we can cancel out our atoms. Avogadro's number goes with the individual components. In this case is atoms. It could also be molecules or particles, as mentioned on that last slide. So atoms cancel. We're left with moles. We need to perform one more step. We use the atomic mass of helium, 4.003. Moles in the denominator. Moles cancel. Performing the math here. We have 6.89 times 10 to the 18. Use that parentheses and EE. You would then divide by Avogadro's number and then multiply by 4.003. And the answer comes out to be 4.58 times 10 to the negative 5 grams of helium. You'll notice that in the first example versus the second example, they are reverse pathways. Don't memorize the pathway, just know how you convert from one to the next and how you get units to cancel. Then you'd be able to convert anything just as long as you know what the equalities are. Again, the equalities of the simplest one I could think of would be like 12 inches in a foot. So you can use any equality to perform a conversion to go either from units like of measurement or grams to moles and moles to individual constituents like atoms, molecules, and particles. So again, one thing just to remember is that a ballpark estimate can help you prevent common errors. For example, the mass in part A is smaller than the molar mass of carbon. Therefore, you should expect a number of atoms smaller than Avogadro's number, which we mentioned this in our last example. Also, the number of atoms in part B is smaller than Avogadro's number. Therefore, you should expect a mass of helium smaller than the molar mass of helium.